Hi, in this video, we want to take a look at two-way ANOVA. All right, so the big idea here is that we have a dependent variable and two independent categorical variables. And the two independent categorical variables define subpopulations. And what we want to do, we want to check to see if the subpopulations defined by these two categorical variables vary across the different subpopulations. And we're going to use analysis of variance to tackle this, ANOVA. So analysis of variance, ANOVA, is a statistical technique used to examine the differences between two or more groups. All right, so in the last video, we looked at one-way ANOVA, and we only had one categorical variable. Now we're looking at with two. Two-way ANOVA, as a specific form of ANOVA, is applied when we have two independent variables that we want to study their effects on the dependent variable. So we have one dependent variable as numeric and two independent categorical variables for the analysis. And we want to check we're interested in the average of the numeric variable. In terms of two-way, this refers to the two factors or independent variables in the experiments. For instance, in a medical study, the effectiveness of a drug, the dependent variable, could be examined against two factors like dosage and genders, and where dosage and gender are our independent variables. Two-way ANOVA not only allows you to determine the main effects of each independent variable on the dependent variable, but also it examines the interaction effects. An interaction effect occurs when the effect of one independent variable on the dependent variable changes depending on the level of the other independent variable. When we have interaction, things are more mathematically complicated. For instance, the effect of a drug might differ between males and females at different dosage levels. The primary hypotheses in two-way ANOVA are: one, the main effects of the first independent variables, the main effects of the second independent variable, and then an interaction effect of the two interacting with each other. All right, so the main effect of the first independent variable. This tests if the mean of the dependent variable is the same for all levels of the first independent variable, ignoring the second independent variable. The main effect of the second independent variable. This tests if the mean of the dependent variable is the same for all levels of the second independent variable, ignoring the first independent variable. All right, so here we're only considering the first independent variable. Here we're only considering the second independent variable, and we're not letting the other ones have any influence on what's going on. Now, on this next one, we consider them both together. Do we get more or less out of the combination? Now, the interaction effect of the two independent variables, this tests if the effect of the first independent variable on the dependent variable is the same at all levels of the second independent variable, and vice versa. If the interaction effect is significant, it means that the effect of one independent variable on the dependent variable depends on the level of the other independent variable. This can complicate the interpretation of the main effects, as they cannot be interpreted in isolation. Two-way ANOVA can be performed with either balanced design, so equal sample size for each combinations of the levels of the independent variables, or unbalanced designs. So we have unequal sample sizes for the subpopulations. Various assumptions need to be met for a valid two-way ANOVA, including normality, independence, and homogeneity of variances. All right, so now let's look at the hypotheses in two-way ANOVA in a little bit more mathematical fashion. All right, so in two-way ANOVA, there are three null hypotheses here. There's one for the first independent variable, one for the second independent variable, and then a third one for them together, the interaction. All right, so the first main effects is saying that and we're going to use A to represent the first independent variable, we're saying that the population average across all of the different subpopulations identified by variable A is constant across the board. This is testing whether the population means of the first independent variable are equal across all levels. And here we're saying we have I levels here, subscript I. Now here we're looking at the main effect of the second independent variable. Second independent variable we will denote by B. And you'll notice I have all equal signs for the subpopulation averages. But this time we have J different levels. So the two independent variables, categorical variables, do not have to have the same number of levels. This is testing whether the population means of the second independent variable, factor B, are equal across all levels. And there's going to be J levels here. Now, that third hypothesis is checking to see, do we have an interaction effect between the two independent variables? And so here, the math gets a little bit more interesting, a little bit spicier. Here, this is going to be the overall population average. This is the population average at level J, regardless of what level we have for the first variable. This is the population average for level I of the first independent variable, regardless of what the level of J is. And here, this is the population average when I'm at level I, level J for both of them. And so we have a lot of subscripts going on in this. So this is testing whether the difference in population means of the first independent variable at each level of the second independent variable is the same across all levels of the first and second independent variables. So mu sub ij is the population mean for the dependent variable at the ith level of the first, so here's subscript I, ith level of the first independent variable, and simultaneously the jth level of the second independent variable. So this population mean takes into consideration the value of both independent variables. Now here, this one, the second independent variable is not considered in this population mean at all, but the first one is. The first independent variable is here. So, and we're just looking at the ith level of the first independent variable, take the population average. Now over here, we take the jth level of the second independent variable, ignore the first independent variable, and take the population average. And now here, this is the overall population average over the entire sample space, not worrying about the value of I and J. The alternative hypothesis, or excuse me, our alternative hypotheses are that at least one of the population means differ across the levels respective of the null hypothesis. So the alternative hypothesis here is that somewhere two levels don't have equal means. The alternative hypothesis is somewhere two levels do not have equal means. And here we have somewhere for some ij, this equation does not hold, that this does not equal 0. Okay, so in previous video, we talked about one-way ANOVA. Now we're talking about two-way ANOVA. All right, so we're kind of stepping into things, and we're stepping into things to get more complicated. We started with we started with t-test, then we did two sample t-tests, then we did one-way ANOVA. Now we're at two-way ANOVA, and the next couple of videos, we're going to make ANOVA even more complicated. So we're trying to baby step into these concepts. So one-way ANOVA, I have one independent categorical variable. Two-way ANOVA, I have two independent categorical variables. Both situations, I'm interested in the average of a numeric variable that is of interest to my study. So one-way and two-way ANOVA are statistical methods used to determine if there are any significant differences between the averages of three or more independent groups. The difference between these two methods lies in the number of independent variables or factors they each consider. So here's a comparison. So when we're looking at one-way ANOVA, one-way ANOVA involves one independent variable. For example, we can study the effect of diet with 3 levels, low fat, medium fat, and high fat, on weight loss. There's only one independent variable, diet. The main purpose of one-way ANOVA is to understand if there's a significant difference in the dependent variable caused by the variation in the different levels of the single independent variable. The null hypothesis of a one-way ANOVA states that the means of the dependent variable are the same across all levels of that one independent variable. And one-way ANOVA does not study interaction effects because there's only one independent variable. We can't have interaction between two variables when I only have one variable. I have to have two variables to do that. Makes sense, right? Now, for two-way ANOVA, two-way ANOVA involves two independent variables. For example, we could study the effect of diet and gender on weight loss. Two-way ANOVA allows researchers to not only investigate the main effects of each independent variable on the dependent variable, but also the interaction effect between the two independent variables. The null hypotheses in a two-way ANOVA state that A, the mean of the dependent variable are the same across all levels of the first independent variable. B, the means of the dependent variable are the same across all levels of the second independent variable. And C, there is no interaction between the two independent variables. And so all three of these are saying, first one, no relationship between the first categorical variable and the numeric variable. Second one is saying there is no relationship between the second categorical independent variable and the numeric variable. And then the third one is saying there's no interaction. Two-way ANOVA provides a more comprehensive understanding of the relationship between the dependent variables and the independent variables, considering both individual and interactive effects. In summary, the choice between one-way and two-way ANOVA depends on the research question and the number of independent variables. Main thing is the number of independent variables. One-way ANOVA is simpler and more straightforward, but two-way ANOVA provides more detailed insights, especially when there might be an interaction effect between two independent variables. All right, now, every single statistical test has assumptions. If our data, if our situation, our theoretical understanding, our subject matter knowledge of what's happening does not support these assumptions, I need to choose a different method to do analysis. So to make sure we do things coherently and correctly, we need to know what the assumptions are. I'm glad you asked, because here they come. Two-way ANOVA makes several assumptions which all need to be fulfilled to provide valid results. First one is independence of observations. Second one is normality. Third one is homogeneity of variances, homoscedasticity. And then additivity. All right, independence of observations. Each subject or experimental unit contributing data to the analysis should be independent from all others. This assumption is usually met through the random selection of samples. Normality. The population from which the samples are drawn should be normally distributed for each combination of levels of the two factors. Normality can be checked through methods such as Shapiro-Wilks tests or by visually inspecting histograms, QQ plots. Next one is homogeneity of variances, homoscedasticity. The variance of data in groups should be the same. This can be checked by using Levene's test or Bartlett's test. And then additivity. The effects of the independent variables on the dependent variable are additive. This assumption is automatically checked as part of a two-way ANOVA because if there is a significant interaction, it indicates that the additivity assumption is violated. When these assumptions are not met, you might need to transform your data or use a non-parametric alternative to ANOVA. As with any statistical test, understanding these assumptions is critical to get a correct interpretation of the results. Now, when I run my ANOVA test, every software is going to spit out an ANOVA table. So let's take a look at one so we have a better understanding of what these are when R, Python, SAS, JMP spits these out. All right, the two-way ANOVA table. In the two-way ANOVA, the output typically includes an ANOVA table which summarizes the results of the analysis. The table is structured to provide a comprehensive view of the main effects of each independent variable and the interaction effect between them. Here's a general structure of the two-way ANOVA table. So we're going to have columns of source of variation, degrees of freedom, sum of squares, mean squares, F value, and then P value. And then we have the main effects, source of variation. Here, we've got two main effects going on. I've got the interaction source of variation, the error, and the total variation. And so then we'll have degrees of freedom for each of these. Interaction degrees of freedom will be the product. We'll have degrees of freedom of the error and degrees of freedom of the total. Here we're going to take the sum of squares deviation from the main effect sample, just one variable considered for the average. For here and here, main effects. Here's the interaction sum of squares. Here's my sum of squares error, sum of squares total. To get the mean squares, what I'm going to do, I'm just going to take this value, divide by degrees of freedom, this value, divide by degrees of freedom, this value, divide by degrees of freedom, and this value, divide by degrees of freedom. Now, what we're going to do is, once again, we're going to take ratios of variances. So we think of these values as being estimates of variation, and we start taking ratios to get our F value. Once I get my F value, I use my degrees of freedom and the F statistic to get a P value, and then I can reach my conclusion of my hypothesis test. So here's what each column represents. The source, this column indicates the different components of the variation in the different variables. Factor A, the first independent variable. Factor B, the second independent variable. Interaction, the interaction effect between factor A and factor B. Error, the within group variability or the variability that cannot be explained by the factors and their interactions. And the total variability in the dependent variable. Next, we have degrees of freedom. This column lists the degrees of freedom associated with each source of variation. We have our sum of squares column. This column lists the total variation that each component contributes to with respect to the dependent variable. We have our mean squared column. This column lists the average variation per degree of freedom for each component. It's calculated by dividing the sum of squares by the corresponding degrees of freedom. Now, the F value, the F column lists the F statistic calculated for factor A, factor B, and the interaction between A and B. It's calculated by dividing the mean square of each factor or interaction by the mean squared error. So what's going to happen is I'm going to take this value, divide by the mean squared error, that's this F statistic. I take this value, I divide by the mean squared error, that gives me this F statistic. I divide this value by the mean squared error, that gives me this F statistic. And then with the F statistic and my degrees of freedom, and for the denominator, all these will have the same degrees of freedom. I get my p-value. The p-value column corresponds to the F tests on these variances. The p-values are used to make a decision about the null hypotheses. If the p-value is less than the significance level, typically 0.05, then we will reject the null hypothesis and conclude that there is a significant effect for that source of variation. By looking at the F values and P values in the ANOVA table, you can determine whether the main effects for each factor and their interaction effects are statistically significant. Typically, if we say that the interaction effect is statistically significant, we will most of the time conclude that all corresponding main effects are also statistically significant. All right, now the formulas for two-way ANOVA, you'll notice that in the table, I didn't write out all the details here. I kept it rather terse just because it gets kind of complicated. I went ahead and slapped it down here. So here's my sum of squares total, right there. All right, sum of squares total. This is the total variation, or this corresponds to the total variation of data. It's calculated as the sum of square differences between each observation and the grand overall mean. So for each individual observation, I subtract off the overall average, I square it, and then I add them all up. Now, the sum of squares for factor A, this is the variation due to the first factor. It's calculated as the sum of the square differences between the mean of each level of factor A and the grand mean, weighted by the number of observations in each level. All right, so here I take the average for each individual level of the first value. So this is like my between sum of squares and one-way ANOVA. So I take each level of variable A, I take the corresponding dependent variable averages, subtract off the overall average, square it, then add it up. And then I multiply by the number of observations to get the right value. So number of observations, and then multiplying by B, same B over here. Now the sum of squares for factor B is the same thing as with A, but now I just switch the role of A and B. This is the variation due to the second factor. It's calculated as the sum of square differences between the mean of each level of factor B and the grand mean. And this is weighed by the number of observations within each level. Now the next one, and this one's a juicy one, we look at the sum of squares for interaction. This is the variation due to the interaction between two factors. It's calculated as the sum of the square differences between the mean of each combination of levels of the two factors and the means of each level of the two factors, weighted by the number of observations within each combination. Okay, that's a lot going on. So you notice I'm taking the average across each combination of variable A, variable B. I subtract off the average of for the respective A value, ignoring the B value, subtract off the average corresponding to the B value, ignoring the A value, and then I add the global overall average. Then I square it, add it up, and multiply by the proper value. Now, the sum of squares error, well, this is the variation that's not explained by A, B, nor the interaction. And it's calculated as the total variation minus the variation attributed to main effect interaction. So boom, we get this nice, beautiful formula. And so now the degrees of freedom. The degrees of freedom are calculated for each factor in this manner. For factor A, it's the number of levels of A minus 1. For factor B, it's the number of levels of B minus 1. For interaction, it's the product of the degrees of freedom of A and B. For error, it's going to be AB times N minus 1. And for the total, it's ABN minus 1. And it'll work out that if we add all these up, it'll equal the total degrees of freedom. Now for the mean squares, I'm just doing division. I'm taking the corresponding sum of squares value, then dividing by the degrees of freedom. So I take sum of squares for A, divide by degrees of freedom A. Sum of squares B, divide by degrees of freedom B. Interaction, divide by degrees of freedom interaction. Sum of squares error, divide by degrees of freedom for error. Now to get the F statistics, I go through, I missed interaction here. But to get the F statistic, I just take the ratio of mean squared for A divided by mean squared error. Mean squared B times mean squared error gives me this one. And then the one that's not here, missing from the notes, is that the interaction mean squared divided by mean squared error gives me the F statistic for interaction. All right, so let's go a little bit deeper into the sources of variation. In a two-way ANOVA, the total variation in the dependent variable is divided into 4 components, each of which corresponds to a source of variation. Here's an explanation for each. Factor 1, the first independent variable. This source of variation is associated with differences in the levels of the first independent variable, factor A. It measures how much the dependent variable varies as a function of factor A. So how much the dependent variable varies as a function of factor A, while ignoring the effects of factor B and the interaction. For factor B, the second independent variable, this source of variation is associated with the difference in the levels of the second independent variable, and it measures how much the dependent variable varies as a function of factor B, while ignoring the effects of the first independent variable and interaction. Now, the one that is mathematically the spiciest, interaction, this source of variation is associated with the interaction between factor A and factor B. And the interaction occurs when the effect of one factor depends on the level of the other factor. The interaction source of variation measures how much the dependent variable varies as a function of the combination. So here we're looking at just one variable at a time. We're looking at just one variable at a time. Here we're looking at the combination of those two. Now, the error as a source of variation, this is associated with the inherent variability of the data that cannot be explained by the two variables that we have for independent variables. It's sometimes referred to as a residual or unexplained variation. Last but not least is the total variation. The total variation in the dependent variable is the sum of the variation due to factor A, factor B, interaction, and error. It measures the total amount of variability in the data. The aim of two-way ANOVA is to partition the total variability in the data into these components and test whether the amount of variation attributable to factor A and factor B and their interaction is significantly greater than the unexplained variation for error. If so, we can conclude that the factors or the interactions have a significant effect on the dependent variable. All right, so now let's focus in on calculating p-values. In a two-way ANOVA, p-values are used to determine whether the results of the test are statistically significant. They're associated with the S statistic for each factor and their interaction. This is how they're calculated. So here, the F statistic, remember the F test is evaluating equality of sample variance. It's evaluating the quality of variances using the ratio of variances. So I'm going to take the ratio of variances. So the variance for A, the variance for error, take the ratio. Variance for B, variance for error, take the ratio. take the variance for interaction, take the variance for error, take the ratio. That gives me my F statistic every single time. So here mean squared A, mean squared B, mean squared interaction are the mean squares for factors A, B, and their interactions respectively. And MSE is the mean square of the error. Under the assumptions that we listed out previously, F statistics follow an F distribution, which is a theoretical probability distribution. Each F statistic has two sets of degrees of freedom associated with it, one for the numerator and one for the denominator. The one for the numerator corresponds to the factor, and the one for the denominator corresponds to the error degrees of freedom. The p-values are then calculated by comparing the calculated F statistic to the F distribution. Specifically, the p-value is the probability of observing as extreme as or more extreme than the observed F statistic under the null hypothesis that there is no effect of the factor or interaction. So I'm looking at observing my F statistic or something more extreme under the null hypothesis. This is done using the cumulative distribution function of the F distribution for a given F statistic and degrees of freedom for the numerator and denominator. The p-value is calculated as 1 minus the cumulative distribution. If the p-value is less than the significance level, typically 0.05, then the null hypothesis is rejected and it is concluded that there is a significant effect of the factor or interaction. Otherwise, there is not enough evidence to reject the null hypothesis. All right, so let's run through an example using R. Let's create a mock data set and perform a two-way ANOVA using R. The data set will have two factors, each with two levels. So we're going to make it pretty easy. I've got two levels of two variables, and I have some numeric variable whose means I'm interested in. So here we, factor A has two levels, A1, A2. Factor B has levels B1, B2. And I'm building up my data, and you can see that I've got four different averages here. Okay, so what this says, by the way that I'm generating it, I've got four different subpopulations, and I'm setting it up so that I have four different population means. So we know that we should, the correct result is to reject the null hypothesis on the main effects. Now, the interaction one, I honestly can't eyeball this myself right now, but maybe, it's maybe not on the interaction. Main effects, absolutely. All right, so here, when I run my analysis of variance, I need to give a formula here. We're saying that the numeric variable depends on whatever is on the right-hand side, tilde, in our formula says that it depends on. And here I want factor A star factor B equal to data, and then we'll get our results. For some reason, R did not print the summary. I'm very disappointed. Okay, I will fix that before class. So in this example, the analysis of variance function performs a two-way ANOVA. The response variable as the dependent variable and factor A and factor B are the independent variables. The star in the formula tells R to include both the main effects of each factor and their interaction in the model. All right, so here the star indicates that I want main effects, and interaction. If I did not want interaction, I would have a plus sign here. A plus sign here would say main effect plus main effect. A colon here would say interaction do not include main effects. Additionally, the interpretation of the p-values is the same as in any ANOVA context, as a p-value less than the chosen significance level indicates a significant effect. In this example, we would look at the p-value for factor A, factor B, and the interaction. Notice that in R, interactions use a colon. Now, there's another way that we can tackle exactly the same problem And that method is using linear regression with categorical predictor variables. All right, so I want to compare two-way ANOVA to linear regression with two categorical independent variables. Two-way ANOVA and linear regression with two categorical independent variables are similar in that both can be used to analyze the relationship between multiple predictors, independent variables, and response dependent variables. The main difference lies in the way the models and how we interpret these results. Here are the key differences. First one is interpretation. In a two-way ANOVA, we are primarily interested in the mean difference between groups defined by two factors and the interaction effect between those factors. We test hypotheses about these mean differences and report whether they are statistically significant. On the other hand, in linear regression, we are primarily interested in the individual coefficients associated with each level of the categorical variable compared to a reference level. This is using dummy variable coding and the statistical significance. These coefficients represent the difference in the expected response from a 1-unit change in the predictor holding all other predictors constant. Now for the assumptions, both two-way ANOVA and linear regression assume independence of observations, homoscedasticity, that is equal variance, and normally distributed errors. However, linear regression also assumes a linearity in the formula, which is the assumption that the relationship between the predictors and the response variables is linear. And that's treating them as the dummy variable presentation. In the case of categorical predictors, this linearity assumption translates to differences between group means being constant across the levels of the categorical variables. Now, the interaction effect in a two-way ANOVA, the interaction effect is treated as a third factor that accounts for the variability in the response. In contrast, in linear regression with two categorical variables, an interaction term can be included that represents the product of the two predictors. So this one's a little like, this is where there's a bigger difference between two-way ANOVA and our linear regression approach. The coefficient of this interaction term quantifies the amount by which the expected change in the response from 1 unit change in one predictor depends on the value of another predictor. This is why I personally like the linear regression approach more than ANOVA, but both are very good. They're excellent choices. Now for output, two-way ANOVA is typically gives us an ANOVA table that provides an F statistic and p-values for the main effect and the interaction. The output of a linear regression analysis includes estimates of the regression coefficients, standard errors, t-statistics, and p-values, along with other several summary statistics like generalized R-squared that helps us to set the overall fit of the model. Once again, this supports using the linear regression approach over ANOVA, but do whatever your stakeholders, your audience wants you to do. In conclusion, while both two-way ANOVA and linear regression with two categorical variables can analyze similar types of data, the perspective and focus of each analysis are slightly different. All right, so now our conclusion. Two-way analysis of variance is a powerful statistical method that allows researchers to compare the average difference between groups that are split by two independent variables that we call factors. Two-way ANOVA is an extension of one-way ANOVA that involves only one factor. The primary goal of a two-way ANOVA is to understand if there is an interaction between the two independent variables on the dependent variable. A major advantage of the two-way ANOVA is that it's more efficient compared to one-way ANOVA. By considering two factors simultaneously, two-way ANOVA accounts for more variation in the data, can yield a smaller error term, and may require fewer participants to detect an effect. Furthermore, two-way ANOVA provides information about the interaction effect between the factor, something that multiple one-way ANOVAs cannot do for us. Interpretation of a two-way ANOVA involves checking the p-values associated with the main effects of each factor and the interaction effect. If the p-value is less than a predetermined significance level, often 0.05, then it is concluded that there is a statistically significant effect. However, two-way ANOVA makes a bunch of assumptions: normality, homogeneity of variances, and independence of observations that needs to be checked. Violations of these assumptions require maybe transforming our data or possibly approaching our hypothesis test with a different test. In conclusion, the two-way ANOVA is flexible and powerful. For example, for examining the effects of two factors on a response variable. Understanding its output can provide valuable insights into the complex relationships among variables in a study. All right. A lot of good stuff here. Next video is going to be on factorial ANOVA. That's where we're going to have 3 or more. ANOVA is going to get even more complicated, but it's good, juicy stuff. This is good stuff. This is all I've got for you. Life is short. Do math.